All right, so here we have another example of solving a trig equation. You'll notice this one took the entire board to pull off, and I probably still admit only barely managed to squeeze it in. So we ignore my circle for just a second. We'll get to that in a minute. Solve with x between 0 and 360 degrees. So that's a tip off. We don't need all the solutions, so we don't have to add the period on. But we do need everything in between 0 and 360, so we will need everything once around the circle. All right, so here's my equation. 2 cotangent squared x minus 7 cotangent x plus 3 is equal to 0. And now this looks a lot like a quadratic, except that it looks like a really pretty nasty looking quadratic, right? Because our quadratic has a cotangent function stuck in the middle of it, and that's really not a happy thing for most people. So here's a little trick you can use to try and make things a little bit simpler at the start of one of these problems. You can do a substitution for the trig function. Okay, I didn't do it on the last example, but I could have, and it would have worked just beautifully. So instead of using cotangent, I'm going to call cotangent x u. You can pick whatever letter you want, just don't pick the letter that's already in your equation, because that'll get really confusing. So I just replaced cotangent with u. So cotangent squared now is not going to be u, but it will be u squared. My cotangent turns into u, and so now I have this much nicer looking equation, and it's just a quadratic. So you can see I factored it, but if you wanted to, you could use the quadratic formula on this, and that would work just fine too. I just really didn't think I probably had room to throw the quadratic formula on here. So I factored it, and because I have two things multiplied together that equal 0, I split them up and set them equal to 0 separately. So for the first one, I add 1, divide by 2, and we get u as a half. For the second one, I just add 3, and I get u is equal to 3. Unfortunately, those are not my answers, right? We need to solve where cotangent is going to be equal to a half and equal to 3. Okay, we're going to undo that substitution now. So we threw the u in just to make this part a whole lot nicer to look at, but now we have to bring back the cotangent. Well, I strongly suspect that none of you know where cotangent is equal to a half, and none of you know where cotangent is equal to 3. Honestly, I don't know where they are off the top of my head, except that I do have the answers on the board, so I guess I do. But only because my calculator gave them to me. So, I want to be able to use my calculator to do this, but my calculator doesn't have a cotangent button. So I would really, really much prefer to just switch it to tangent. We know that cotangent and tangent are reciprocal functions. So if I flip over the 1/2 to 2, that's my tangent value. So I can switch from cotangent to tangent just by flipping that other side. And then I did the same thing here. I switched from cotangent x equals 3 to tangent x is equal to a third. The advantage is now I can use my calculator, right? I can say, oh, if tangent x is equal to 2, that means that x is equal to the tangent inverse of 2. And so we're going to use this little trick a lot in these sections. We have, in this case, tangent equal to a number. We say, oh, well, if we want that thing on the inside of tangent, let's use a tangent inverse of that number to get it. And you can see I did it for both the 2 and the 1/3, and they gave me 63.4 degrees and 18.4 degrees. So we're going to pause here in this problem for just a second, because this is a really neat little trick. That last problem I did was in radians, and I suspect that a lot of you don't care as much for radians. Unfortunately, I asked for exact answers. And so you're like, oh, now I have to figure out everything about this circle going around. Well, guess what? You could do it in degrees and then convert your answers when you were done back to radians. So for those of you who don't like going around the circle in radians, which we did on the last problem, you could instead do it in degrees, and then just don't forget to change it back to radians. All right, so anyway, let's get back to this. So we have these two solutions that we found. But here's the thing, and I have this circle drawn here, and hopefully you can read it. If not, I'm going to talk you through it anyway. These two angles are not the only place that this happens. There are going to be actually 2 more places where it happens. So on my circle here, I put an angle of 63.4 degrees. I know it's somewhere in the first quadrant, so remember, it doesn't need to be placed exactly. It just needs to give us an idea of, where is this thing? So I know that tangent is positive in quadrants 1 and 3. So I know that there's another angle down here in quadrant 3 that will also give me a tangent value of 2, okay, because since 2 is positive. So that angle has to have 63.4 degrees as its reference angle. So this is the opposite of the way we did reference angles. For reference angles, we said, hey, here's a big angle. Let's subtract the 180 to find out what that little angle is. We're going to do it backwards. We have our big angle, we have our 180. Let's add the reference angle that we already know. And if you do, if you add the 180 to 63.4, you get 243.4 degrees. And there's another angle. And the exact same process with the 18.4 degree angle will get you the 178.4. And so there are 4 solutions here: 63.4, 18.4, 243.4, and 178.4. All right, 2 more little examples that have some kind of quirky stuff going on. So let's look at this one. All exact solutions in radians for sine of 3x is equal to 1. So I'm going to use the inverse trig function, even though we probably don't need to. You could go back to section 5.2 and find where sine is equal to 1. But what I'm doing here is I know that the inside, the 3x, has to be equal to the sine inverse of 1. So I know that sine inverse of 1 is pi over 2. If you think about your circle, the only place sine is 1 is at the very top of your circle at pi over 2. So I have 3x is equal to pi over 2. And then you can see I'm getting rid of the 3. So I divide by 3 here, and I just multiplied by a third on the other side, because that was easier than dividing by 3. So pi over 2 times the third gave me pi over 6. Now, I want all exact solutions, so I need to add the period on. But this problem has a different period than most, because you'll notice that we don't have sine of x, we have sine of 3x. And so if you think back to section 5.5, when we did the graphs of sine and cosine, we know that the period here is going to be 2 pi divided by 3. So when instead of adding 2k pi, I add 2k pi over 3 to change that period. And that will get me every single solution that there is for this one. Very conveniently, there's only one place where sine is equal to 1. It's only at pi over 2, at least going once around the circle. So that's why there's only one set of solutions here, whereas so many of ours have had a lot. So that's a quick little one, but it really is just playing on the fact that we have a number inside here, and that's okay. It just adjusts the period down here at the bottom. All right, last one, and this one is a really kind of messy little problem. So we are set up here is that we want x to be between 0 and 360 degrees. We want exact solutions. And that's not going to be too bad. We are in degrees, so that usually makes people happy. But here's my problem. Cosine squared x minus sine squared x is equal to 0. Oh boy, that's tricky. And it's tricky because it has both sine and cosine in it. And so that's our starting point. We really can't have both sine and cosine. Anytime you have one of these equations, if it has 2 trig functions, that's just not going to work. And so you're going to have to try and come up with some way to fix it. So here's how we fix this one. I know from my Pythagorean identities that cosine squared x plus sine squared x is equal to 1. Well, that gives me a relationship between cosine squared and sine squared. So I solved this for sine squared. I just subtracted the cosine squared x. So I know that sine squared x is equal to 1 minus cosine squared x. And I bring that back, and I'm putting it in place of the sine squared now, because I know that sine squared is equal to 1 minus cosine squared x. So we now have an equation that only has cosine in it, and that's much better. All right, so if you distribute your minus sign, a minus and minus makes a plus. So 1 and 1 gave me the 2 cosine squared x. And obviously I have the minus 1, and it still equals 0. So now I want to get that cosine all by itself, so I'm adding the 1 and dividing by 2, and that gets me all the way down to here. Cosine squared x is equal to half. I take the square root. So I have plus or minus 1 over the square root of 2, because of course the square root of 1 is just 1. So I didn't really bother with that. And then I rationalize the denominator. It's hard to see because my handwriting is lousy, but I do have here plus or minus the square root of 2 over 2. And so we say, okay, well, where is cosine then equal to positive or negative square root of 2 over 2? You could do it with an inverse trig function. Right? I mean, you could type in cosine inverse of square root of 2 over 2, and that would get it for you. But that's one that we should probably know. It is 45 degrees in that first quadrant. And then because we have the plus or minus, we need all those angles that will have 45 degrees as a reference angle. So this is similar to the one we did on the last board. We just need to figure out what all these other angles are. And so since this one's 45, this one right here would be 180 minus 45. There's 135. This one down in the third quadrant would be 180 plus 45, giving me 225. And the last one over here in the fourth quadrant would be 360 minus 45, and that's 315. And so there we go. Trig equations. They're usually not anybody's favorite, but do the work. You can do them, and have fun.